Hello, my IB physicist, Ms. Getz here. Today I'm going to go over the shelving sheet for Unit 1, so Unit 1 Patterns and Predictions. This is in your IB Physics binder and it's page 1.8. It's the last page in Unit 1. And every single unit for IB Physics, I have a shelving sheet for you to help you organize your thinking and really try to understand all of the different concepts that we've learned in that unit. So we're going to go ahead and I'm going to help you go through this shelving sheet, filling it out. And I really highly recommend filling this out with me. I'm not going to fill them out with you every single time we do something together, because I want you to go through that process to try to understand the material yourself, and you can ask me questions, of course. But I figure this unit, it would be really helpful for you to have me help you out at first. So we've looked at 3 labs in IB Physics so far this year. One of them is not on this sheet, and there is a lab here that is superfluous that we aren't doing. So this is not applicable, NA, for DL. We are going to study this mathematical pattern, the quadratic pattern, which you've probably learned in math classes, y equals ax squared. But we're not going to dig into that right now, right here in this unit. The first pattern that we started with was our pendulum lab, and that turned out to be a flat line. And then our second lab is our rubber band lab, where we were investigating how does the mass hung on a rubber band affect its stretch. So that was our whole guiding question, its stretch. And so that means that our independent variable, the thing that we were changing, was the mass that was hung on the rubber band. So mass hung. And then the thing, wow. I'll write that slightly more neatly. Mass hung. And then the dependent variable was the stretch of the rubber band. Stretch again. There we go. So we have our independent variable, we have our dependent variable, and this turned out to be a linear pattern. And so you found a linear pattern. Technically, what is written right here is proportional because it's going through 0, 0. We know that it should go through 0, 0, but it isn't necessarily always going to. And so that means that we have a linear pattern here. So I wanted to think about, well, what physical meaning were we able to glean from this? What are we able to say physically about our rubber band from our graph here? And the big idea that we were able to take away was that the slope of the line is the physical stretchiness, a very technical term, stretchiness, might not even be a real word, of the rubber band. So it had a physical meaning, and this was the slope of the line, or M, the slope, or we actually maybe called it A as the slope of the line. So that tells us about the stretchiness of the rubber band. We also could tell from the y-intercept, B, that tells us that when no mass, that we should also have no stretch. And again, this is making physical meaning of the equation. What does the equation tell us physically about the real world? And again, our mathematical pattern here, I'm going to jot down, is y equals mx plus b, or I could write it as y equals ax plus b. Again, it doesn't matter which variable is representing mass. The mass is going to be an actual numerical quantity. So then I have a visual representation here for you that's telling you that if x doubles, if it increases by 2, then y is also going to do that same thing. It's also going to increase by 2. That's my visual representation. And so I also would like you to try writing that out in words. So take a moment, maybe pause the video right now, try to write that out in words. Maybe try to write that out in words for this next one, which has x tripling. So I would write that out in words by saying, if x triples, then y will also triple. The key idea in our linear proportional relationships here is that if one thing happens to x, that exact same thing is going to happen to y. So that's our linear relationship of our rubber band lab. If we were doing this at school, it would have been with a spring, but it would have been pretty much the same lab. So then this last lab that we did was our paragraph lab. And in this lab, we were considering the research question, how does the width of a paragraph, so how does the width of a paragraph, I'm going to use the abbreviation of paragraph so I don't have to write it, affect its height. So we're saying, how does the width of a paragraph affect its height? So that means our independent variable is width. And honestly, we could have gone either direction with this. We could have said, how does the height affect the width? Either one is equally valid. And then our dependent variable, in the way I have phrased the question, is height. And so what we found in this one is that there's actually an inverse relationship between these two things. So mathematically, an inverse relationship looks like y equals a over x. And graphically, it looks like this down swoopy thing that's going on here. Notice that our axes labels are wildly incorrect here. And that's because if we were in school, we might have done this different lab about resistance. But here we would have width, and then we'd have height on the y-axis. Sweet. So then you want to say, well, what did this mathematically, physically tell us about the meaning of this relationship? I found a relationship that told me that the height of my paragraph was equal to some number. My number was 71 over the width. And what does this tell me? So if you were in class on Thursday, we are talking about that then in class on Thursday. But if you weren't, the way that I really like to make sense of this is to actually rearrange this equation. I'm going to move width over to the other side so that my equation actually becomes width times height equals 71. And that should give you a little bit of a clue as to what this is. And in fact, another clue you can get is adding the units on here. The units on this number are centimeters squared. So that means that this number is actually telling us physically something about the paragraph, and it's telling us about the area of the paragraph. And so I'm going to describe that as a physical meaning. So that's the proportionality constant. Proportionality constant is the area of the paragraph. Again, shortening paragraph. That is the physical meaning that we can make from this mathematical equation describing this real situation. And so physically, if we know that proportionality constant, we know the area of the paragraph. And that makes sense, again, when you think logically about what this equation is really telling us. It's really telling us the width times the height equals a constant number, and that is the area of that paragraph. So mathematically, we can represent an inverse relationship this way. So if I double x, if I make x multiply by 2, then y is actually going to do the opposite thing. It's going to multiply by 1/2. So x doubles, y halves. Then what happens if x triples? Take a moment and try writing that in words. What happens if x triples? So I would write in words, if x triples, then y, it's an inverse relationship, so y it will go down by 3 will decrease by 3. Or decrease by 3 is not good. That implies subtraction, and you definitely don't mean subtraction, Ms. Getz. If x triples, then y divides by 3. So it does the inverse thing that happened to x. That's why it is called an inverse relationship. So pause if you need to finish writing, and I'm going to go ahead and flip to the next page of paper and finish writing myself. Hopefully it'll work. We'll see. All right, my IB physicists, this is the 3rd time I'm recording this. Let's hope it works this time. I don't think my stressed out little brain can handle this anymore. So this is page 2 of our shelving sheet. We already looked at page 1, looking at some mathematical patterns. And page 2, we're going to be talking about uncertainties. And we're going to be thinking about how we deal with them, how we propagate with them, and so on. So take a deep breath. Cross your fingers that my recording works. Obviously, if you're watching this, it did, so TBD. Hopefully there'll be no swearing in this video this time. So we're going to start out with table number 2, and in table number 2, we are looking at random error. And random error is all about how spread out your data is. So it's the spread of data, how far spread apart your data that you have collected is. And it is the larger of 2 things. It's actually what your error bars are going to be. So another way you can think about this, here is your error bars, just as a nice cue in. So it's the larger of 2 things. It's the larger of either our measurement uncertainty, or our statistical uncertainty. So it's the larger of those 2 things. And as you might recall, measurement uncertainty is determined either by the limit of the instrument, or some sort of procedure error. And that's where we have to be really, really specific about what you mean by procedure error. It has to be a reasonable estimate. For example, if I'm going with procedure error as my measurement uncertainty, that might happen when you're timing something and you're saying, because a human is clicking with their finger, there's human reaction time, which is a procedure that has some inherent uncertainty in that way you are doing it. Otherwise, you're going to want to use the limit of the instrument, which you might recall is half the smallest increment for every measurement taken. So like for a meter stick, that's going to be half of 0.1 twice, which is actually 0.1 centimeters for any meter stick. And this is random error. And random error tells us about the precision of our measurements. How precise are they? Not how right or wrong are they, but how precise are they? Just as for completeness, include that the statistical uncertainty is 1/2 the range of multiple trials. So you're only going to have statistical uncertainty when there are multiple trials. If there aren't multiple trials, it will not be any statistical uncertainty involved. Okay, so that's random error. It tells us about the precision of our experiment. Systematic error is that something like constantly went wrong in your experiment. So you have something consistently going wrong, wrong in experiment setup. And so systematic error tells us whether or not our experiment is accurate. And the key to being able to tell if you have systematic error is that we're going to compare to a known. And what I mean by known here is that something that we know. For example, in our rubber band lab, we knew that if we hung 0 mass on the rubber band, it should have 0 stretch. So that means that we know the y-intercept should have been 0. So systematic error, often you'll look at a y-intercept. That's often something that we know. There also might be a measured value that we know. For example, we know the acceleration due to gravity is 9.8 meters per second squared. And so that's a comparison that we can make in future labs when we're finding the acceleration due to gravity. We know what it should be, so we can compare our results to that number. If we don't get that number, that means that we had systematic error. Something was wrong in our experimental setup consistently. Not just randomly, that would be random error, but every time we gathered data, there was some sort of consistent error. So those are our 2 different types of errors that we can have, systematic error and random error. And whenever we have errors involved, in fact, these are usually going to be uncertainties on our measured quantities, we need to be able to propagate those uncertainties. So to do that, if I'm adding or subtracting numbers, I am ultimately just going to add their absolute uncertainties. Absolute uncertainties. Now, if you wanted to, you could go ahead and write out the whole equation where you're like A plus or minus delta A plus B, blah, 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 blah. But I find it actually a lot easier to just think about this in terms of words, because I know what adding means. And I know what absolute uncertainties mean. So I'm going to add those together. If I am multiplying or dividing numbers that have uncertainties, we're also going to be doing some adding, but this time we're going to add the percent or relative uncertainties. Percent is hard to spell. Uncertainties. So I'm going to be adding these percent uncertainties together, because when you're multiplying or dividing numbers, you're actually totally changing their place values. So it would make no sense to actually keep the place value by using the absolute uncertainty. So then we care about the percent uncertainty, or like how much of the number is uncertain. And so those will add together. Okay, so then powers are where things get a little bit complicated. And a power is when I have like x to the n is the power. These are exponents from math class. So when we have powers, we're actually going to multiply the percent uncertainty, you can finish the word, by the power. So for example, let's not do x to the n because that's a variable, but if I have x to the 3rd power and I'm trying to propagate the uncertainty, I'm going to multiply the percent uncertainty by 3. That's the power that's involved. So powers aren't so bad, actually. They're really very similar to multiplication and division, and that's because actually when you're using a power, you're either multiplying or dividing multiple times. That's what a power actually is doing. Okay, cool. So then let's go ahead and move on to table 4. So table 4 is down here, and it's maybe not labeled. I don't know why. But table 4 is looking at systematic and random errors in actual physical representations. So we're going to look at 2 different physical representations. We're going to look at the bullseye representation and the graphical representation. So what will that look like on a graph? What will that look like on a bullseye? Okay, so let's start off with, I think, the easiest case. That's when we have no systematic error and no random error. That's essentially like perfect lab data. On a bullseye, that means that all of my darts or bullets or whatever are ending up in the center of the bullseye. They're all in the center circle, they're all really close together, etc. On a graph, that's going to be a little bit different looking. On a graph, that means that my data points have very small error bars. You can't even really see the teeny tiny little error bars I'm drawing here. So they have very small error bars. They don't have a large spread in data. They don't have very much random error. And that also means then that my min and max lines are not very far apart from each other. They are, in fact, quite close to each other. That is showing us that there's no random error. The thing that's showing us that there's no systematic error in this graph is that it is linear and it's going through 0, 0. And this is kind of like a special case. Well, it's not that special. We're going to linearize graphs eventually, but we won't get there for a few units. When we have something, a graph, typically it's going to be going through 0, 0. I'm making a wide sweeping generalization there, but we're going to roll with it for now. It's okay. So in this experiment, it is both accurate and precise, which actually means I could have just circled both instead of both, but that's fine. So we can see that we're going through 0, 0 as our y-intercept. We have very close together min and max lines. We don't have a very large percentage uncertainty in our slope value, and all of our values are really closely grouped together. So then if we have no systematic error, that means our experiment is going to be overall correct, but we do have random error. What that means is on a bullseye, I'm overall getting the right answer. If you averaged out all of those darts, I'd be doing pretty well. But if we look at individually, they're not exactly all spot on. Then on a graph, what that means is I have a lot of random error, I have a lot of spread in my data, so I'm going to have larger error bars. So here we have larger error bars. I should have more data points, but I made them too big. And so that means that my min and max lines are going to be pretty spread apart from each other. They're going to have a large percent uncertainty in the value of the slope, but notice that the y-intercept here is going through 0, 0. So we have no systematic error. That means that our experiment is accurate, but it is not precise. Whew. Okay, so then let's do the opposite case. If we do have systematic error, but we don't have random error. So that would mean that when you are throwing your darts at the dartboard, you're all getting them to be very close together. Wow, look at that. But actually they were supposed to be over here. Whoops. On a graph, on data that we get in a lab, what that's going to look like is that I'm going to have, again, pretty small error bars. You can barely see how tiny my little error bars are. And my min-max lines, when I draw them in, are going to be, again, fairly close. Fairly close together. Yeah. But notably, we're not, our y-intercept here for our average y-intercept is not going through 0, 0. We're totally missing the mark on 0, 0. And so that means that our experiment is precise, but it is not accurate because we have systematic error. Then if we have both systematic error and random error, that's when our data points here are really spread out. You probably don't want to play darts with this person. I'd be worried about getting hurt. And we're going to have pretty large error bars. Again, these are really exaggerated to be quite large. So that means that when I have my min-max lines, my maximum slope line, no, that doesn't go through all of your error bars. Maybe like that. My minimum slope line, like that. So again, noticing that there's a large spread in the min-max lines, that would mean we would have a large percent uncertainty in our slope. And so this set of data is neither precise nor accurate. Okay, so the last thing that we're going to cover here in Table 5 is really getting a sort of summary of relative uncertainties versus absolute uncertainties. So relative uncertainties are also going to be called percent uncertainties. In fact, I'm going to call them percent uncertainties most of the time and not, I mean, sometimes relative uncertainties. I'd be used to really delineate the difference between the two of them. Relative uncertainties are just percent uncertainties that aren't turned into percents, but that's kind of extra and annoying. So let's just go with percent uncertainties. So when we have something that is a percent uncertainty, a key way to tell that it is a percent uncertainty is that it has a percent sign. And you might be like, well, duh, Ms. Getz. Yeah, I know, duh. That's the key way to tell you have a percent uncertainty. The key way to tell that we have an absolute uncertainty is that it has the same units. And I got cut off. So I took a picture. So like I was saying, it has the same units when we have an absolute uncertainty as the value. Then you want to make sure that you know how do you get a percent uncertainty from an absolute uncertainty. And I did a quick little recap of if you're struggling with the notation that you see sometimes when we just have a variable. So here I have x, that's our value, and then plus or minus delta x. This delta is this triangle is the Greek letter delta, and it means change in. So it's actually used pretty frequently in science to indicate a change in something. So here we mean a change in x, and that means the absolute uncertainty of x. So if you're confused by that notation, it's really helpful to make sure we have our value and our absolute uncertainty. So we can find our percent uncertainty by taking our absolute uncertainty and dividing by our value. So that would be delta x divided by x and then times by 100% to turn it into a percent uncertainty. Similarly, we can also go from our percent uncertainty to turn it into an absolute uncertainty. And this is going to happen when you are trying to propagate some uncertainties and like maybe you have to do some multiplication first and then you have to do some addition. So you really have to start by turning the percent uncertainty when you found the total percent uncertainty back into an absolute uncertainty. So I'll take my percent uncertainty, divide it by 100, and then multiply by the value. So that we're going to get something that again has the same units as whatever value it is we are looking at. So my IB physicists, I'm sorry this video has been a little bit delayed. It has caused me great angst at a time where we don't need more angst. But I hope it was helpful for you, and I'm sorry that it is really a little bit too long. Maybe you watched it on times 2. Definitely consider doing that. Good luck, guys. Let me know if you have any questions.